Welcome to Show New Channel. Please like, share, and subscribe to my channel. My today topic is work, energy, and power. So we will first talk about work. Work can be described by two things. First is constant force and variable force. So we will first see constant force. This is the best example I have got that about a boy is providing a constant force to this object. The first we will see what is actually the work is. Work definition is the work done by a constant force is uh, is defined as the scalar product of force and the magnitude of displacement under the influence of force. So it is W equals to F dot D. So you see dot, that means it is a work is a scalar quantity. So when we have to convert this dot, we have to multiply cos theta to get magnitude. So FD cos theta. This is a work done. The second is work done by a variable force. So we will see one more example which is of variable force. You can see let us assume that a variable force act on a particle. The variation of force and the displacement due to the influence of force is shown in this figure. And by this you can make the how by various at different point we require that different forces are being applied to this bucket. So we have formed this graph which is F into displacement, where we observe at different displacement we have different forces. So this is the shaded area are the area of the under the curve, which is the work done of this variable force. So to calculate this we have to integrate this from if we have to find this point to this point how much work done is done, how much work is done. So we have to integrate from 0 to s, and dot product of f into dx. So we get the total work done by a variable force. So by this we can obtain work done of any application, whether it is a constant force or a variable force. Now we will see energy. So energy is a physical quantity which enable a work system to do work, and we need energy for any kind of means we whatever work we have to do. So there are many form of energy in the universe, but in case of mechanical energy, we have two broadly means two. One is kinetic energy and second one is potential energy. So we will see one first kinetic energy. So in kinetic energy, we can see this example. The kinetic energy of a body is the energy possessed by the body by virtue of its motion. So it is the kinetic energy formula is half mv square. Where v is the velocity of the body, and this one very interesting thing in this formula that m and v is always going to be positive. So kinetic energy is always positive, and it doesn't depend on the direction of motion whether you are going up or down. It is always in positive, and the relationship between kinetic energy and momentum is k equals to p square by 2m, where p is the momentum. And by this equation you may find similarity in parabola equation, that y equals to 4x, something like that. So you can make one parabolic graph also, by which you can form a relationship between k and p, which is this k. This is a parabola curve, and k equals to p. K versus p. If you can make one easier form of means another graph also, in a straight line, which is of k under root k and p. Just removing the square to here, So you can form this is directly proportional. You can see K is directly proportional to P, so you can make this graph too. So now after kinetic energy we will see potential energy by this example. A girl is holding a ball. So in this potential energy of a body is the energy possessed by the body by virtue of its position relative to the other. So it is V equals to mgh. So where h is the height of the position possessed by the body relative to the ground. This g is acceleration, gravitation, and this is mass. So acceleration or gravity of Earth is 9.81. So this is another example. Means we can see when a girl release this ball from her hand, this potential energy transforming into a kinetic energy. So this is a best thing we can see how potential energy can be converted into a kinetic energy. Now, you have seen this vertical form of potential energy, but there is another form which is a horizontal form of that is potential energy. That by which by this spring example, I can explain you how potential energy is there in spring. So assume this is a block which is it is initially it is in a relaxed position. You are not touching anything. Now after some application of pressure, you compress this block, and this spring got gets compressed here, and after some applying pressure, you release this block, and you will find that there is extension of this block from this x to this position. So you find that there is some form of energy which is got possessed in this block. So by this you form a relation which is u equals to half into kx square. This k is stiffness of the spring. This is it. That's why spring stiffness play a very important role whenever you as because as per your application need, this k is very important. So this k is a stiffness of the spring. So potential energy u equals to half kx square, where x is the this distance. So how much distance it get extended. So by this equation we can find potential energy of the spring. Now a very important law in mechanical energy of which give a relationship between kinetic energy and potential energy is the conservation law of mechanical energy. It states that for conservative forces, the sum of kinetic energy and potential energy at any point remain constant throughout the motion, and it doesn't depend on time. So you can see at every point, that either 1 or 2 or 3, the total sum of kinetic and potential energy is always constant. This is not only limited to mechanical energy. In other form you will find this similar. First, in heat energy we can see the total energy of an isolated system remain constant, so the energy can't be created and can't be destroyed. And in chemical energy we can see that there is a change of form, but total energy of in a chemical reaction remain constant. So here also energy remain constant. In electrical energy, the total electric charge of a system remain constant. The charge can't be created and can't be destroyed, just like heat energy. And in the last means in the another form which is in nuclear, where we have found that in a nuclear reaction total mass of the reactant or the starting material must be equal to the mass of the product. So you will find that there is similar amount of mass in the starting material and the final product. So the mass can't be destroyed or nor created. So these are all conservation law of energy. So we will see work energy theorem. how they are means this is also a very important topic. So the work energy theorem, first we will see about by a constant force. So it states that the change in the kinetic energy of a particle is equal to the work done on it by the net force. So if consider this equation, W equals to kf minus ki. This is the final kinetic energy, and this is initial kinetic energy. So just by the difference of final and initial kinetic energy, we can find work. So this is the work energy theorem. Then how we can find variable forces, this work energy theorem. So let us assume a variable force working from position xi to xf. Then according to the work energy theorem, yeah, you have seen this example of the bucket. Same, nothing different. Wait, I am showing you once again. This example you can relate here also. This work energy theorem applies, and how I'm showing you right now. So this just we have to do final kinetic energy minus initial kinetic energy same, but here it is shown as x1 to x2 f dx, and this is dk. So you know this is change, we can write as a dk. So from initial kinetic energy to the final kinetic energy, we can find this. So this how we can find final this total work from this equation by just integrating from final to initial point. Now in last we will see power. So power is a rate of work done, and it is also defined as the work done over a time period. So it is generally expressed as E by T or W by T, where E is energy and W is work done. So this P equals to dW by dt. This dW can also be written as F into dr dot dr by dt. This is power. Now from this equation we can see dr by dt, and we know that displacement per unit time is velocity. So this power can be written as force into velocity. So this very important to note that power unit is watt, force newton, velocity is having a unit of meter per second. So and joule is the base unit of work. So 1 joule equals to 1 newton meter, and 1 watt equals to 1 joule per second. So the SI unit of power is watt. Now most of the question you will see this unit in term of horsepower. So 1 HP equals to 746 watt. As you know, US customary units are generally expressed in HP. So you need this conversion factor to solve any problem. So now you can see that many times this power, this watt, it can be defined unit of this is kilowatt hour, are often used in electric bills, but this is not a unit of power, this is a unit of energy. So so thank you for watching my video.